Our next type of polymer is that of lipids. So we mentioned that carbohydrates are comprised of carbon, hydrogen, and oxygen. Lipids are a little bit different. They're mainly comprised of carbon and hydrogen. So no oxygen is present, all right, or typically not present. And that's because the carbon and the hydrogen are going to be shared equally, or I should say the electrons amongst the carbon and the hydrogen are going to be shared equally. And that is going to lead to nonpolar covalent bonds. So if they're mainly comprised of nonpolar covalent bonds, the electrons are shared equally amongst the members of the bonds. That means that there's no charges to attract a water molecule. So water, if you remember, has partial positive and partial negative charges because of the oxygen that's present in the water molecule. So that's going to make it polar covalent. If it has charges, it's going to attract other charges, right? Opposites attract. In this case, the members of the molecule are comprised of nonpolar covalent bonds, and so they're not going to attract water at all. So the main characteristics of members of the group of lipids are the fact that they are hydrophobic. Hydrophobic means that they are water-fearing. So hydro for water and phobic, think about if you have a phobia of something, you have a fear of something. So lipids are hydrophobic, they're water-fearing, they don't attract water at all. And that's because they don't have any charges to attract water. They don't have a positive charge or a negative charge. All the electrons are shared equally. So for lipids, there's not necessarily a single monomer that we find that we can use to build all the different types of lipids. We're going to find that we have these kind of hydrocarbon chains that make up lipids, but we can also have kind of a ring-like structure as well for our lipids. We can talk about triglycerides as an example of a lipid. So you probably have heard of triglycerides as far as your diet is concerned. And a triglyceride consists of a glycerol group. So if we're talking about subunits, so this little circle here represents the glycerol, and then it has 3 fatty acid chains to it that are coming down off of it. So these squiggly lines represent the fatty acids. So you can think of fatty acids as kind of a subunit in a way, and fatty acids are basically carbon to carbon backbones with hydrogens coming off of it. All right, so we still see some oxygen down here, right? But for the most part, this is going to be 16 to 18 carbons long with hydrogens coming off of every single one of those carbon atoms. And that makes up a fatty acid. So a triglyceride is tri for 3, meaning it has 3 fatty acids and a glycerol group. In the coming chapters, we're going to talk about a molecule called a phospholipid. So phospholipid. So it's a lipid with a phosphate group. So here's the phosphate group at the top there. We still have the glycerol. And in this case, we only have 2 fatty acids that come down off of that glycerol. This is going to be important to know the structure of this molecule because we're going to use it to create membranes. And that's what you see in this image here, is what we call a phospholipid bilayer. So it's basically 2 layers, right? There's layer 1 and there's layer 2 of phospholipids. I like to call a phospholipid the model of a phospholipid, the egg on legs model, because it looks like an egg where you have that glycerol and the little phosphate, I guess, if you want to put a little hat on them there for the phosphate. And then you've got the 2 legs, which are the fatty acid groups. So with lipids, we also have other types of fats. So I'm sure you have also heard of saturated fats and unsaturated fats. Saturated fats, if you think of the word saturated, think of it as meaning that the fatty acid, all right, is just saturated with hydrogen. So this is showing our fatty acid. It looks a little bit like a caterpillar there. And we said it has this carbon to carbon to carbon to carbon backbone, and then we have hydrogens coming off of each one of those carbon atoms. So every single carbon is basically saturated with hydrogens. Lots of hydrogens coming off of each one of these. All right. So think of the word saturated as meaning saturated with hydrogen. And there are single bonds between the carbon atoms because carbon can accept or share 4 electrons. So there's 1 bond there, 2 bonds, 3 bonds, and there's the 4th bond. And each one of these is a case where it's just a single bond between each of the atoms. Now, saturated fats we recognize as being solid at room temperatures. So if you think of when you're frying bacon in a pan and you get kind of all this bacon grease that is left in the pan. So it might be kind of liquidy because it's hot, but as you allow that bacon grease to cool down, it's going to solidify. It becomes a solid. And that is a saturated fat. So if it's a solid at room temperature, it's saturated. So the idea is that we've got these long straight chains, and we can kind of pile these fatty acid chains on top of each other and compress them really nicely into a solid form. Okay, so saturated fats have single bonds, they're saturated with hydrogens, and they are solids at room temperature. So we want to compare that with unsaturated fats. So unsaturated fats, if we look at the structure over here, we've got that carbon backbone, and then all of a sudden we have this area where there's no hydrogens. And what has happened is there is a double bond right there between 2 carbon atoms. So instead of sharing 1 pair of electrons, they're sharing 2 pairs of electrons. And therefore the hydrogen is not needed. So that double bond right there causes the molecule to actually bend at an angle. So here you see the molecule going straight, and then all of a sudden it bends off down there, and that's due to the fact that there is 1 bond and 2 bonds right there between those 2 carbon atoms. So this is just a different representation. This is what we call a ball and stick model. So the black is the carbon and the white is the hydrogens. Okay. So that double bond causes the fatty acid to go off at an angle. So we typically see that unsaturated fats are liquid at room temperature instead of being solids at room temperature. So why are they liquids? Well, it's much harder if you've got molecules that are bending off at different angles. Right, just trying to draw some shapes here. And it's much harder to compress them into a solid if they are kind of jutting off at different angles. So your unsaturated fats are liquid at room temperature, and they're not saturated with hydrogen. So if they're liquid at room temperature, then this is going to be a lot of your oils, right? So your vegetable oil, your canola oil, your cod liver oil, and a lot of different fish oils are unsaturated fats. And then lastly, we come to some other types of lipids. what we call waxes and steroids. So you can see the ring-like structure at the top here of a steroid. So we don't have that long fatty acid chain that we were talking about earlier for our saturated, unsaturated fats. So steroids have ring-like structures. And examples of steroids are cholesterol, is probably the best well-known one. Right? So we tend to think of cholesterol as being something that's bad for us, but cholesterol is actually a component of cell membranes, and it's a required component of cell membranes. So it's very important to have that. Cholesterol is also the precursor for a lot of sex hormones, so they're very important as well. Waxes are also types of lipids. So we think of wax, once again, as being hydrophobic, a characteristic of this group. The fact that they are water-fearing, they don't mix well with water. So plants will cover the outside of their tissue, their epithelial tissue, with wax to prevent water loss. And then as far as the purpose of our lipids, they're mainly for energy storage. So they can pack a lot of energy within the structure of the molecule. They're actually much more efficient at storing energy than carbohydrates. So we said carbohydrates can store energy, lipids can store energy, but they can store at least twice the amount of energy as a carbohydrate does. So they're much more efficient on that level.